Hi, my name is UTHAYAKUMAR, metric number 211090989. So today I will be presenting on the FYP demo presentation, which is on my project modeling and simulation of EV charger for bidirectional charging operations. So the project objective is to develop and simulate the MATLAB simulating model of a single phase bidirectional EV charger for bidirectional operation. Second is to analyze the variation in voltage and current across the grid during the bidirectional charging operation. And third is to analyze and evaluate the battery side performance connected to the EV charger, observing key parameters such as battery current, voltage, and state of charge during the bidirectional operation. So the project approach is simulation-based modeling, and the main tool used is the MATLAB Simulink. So why MATLAB or Simulink is chosen? Because first of all, the software is widely used by researchers and industry. It's well known for its accuracy and reliability of modeling and simulations. Second, it offers vast range of components in existing library to construct an EV bidirectional charger model. Third, it provides accurate time domain switching simulation with real-time scopes. Fourth, it cut costs and time for building prototype hardware for modeling and analysis. So this is the block diagram of simulation model setup. So it begins from single phase grid supply to LCL filter into bidirectional AC-DC converter and into the DC link capacitor, the bidirectional DC-DC converter and EV battery. In the middle, it's being controlled by the controller. So this is the simulation model setup, the interface of MATLAB Simulink. On the left, you can see the library browser where we can look up for the components for the model, and we can drag and drop and set the values for parameters, and also we set the simulation time and we can start running by pressing the run simulation button. To proceed with, we have to calculate the simulation parameters for the modeling. So it begins from calculating the LCL filter, bidirectional buck boost converter components, and also the DC link components. So this is the simulation parameters that we obtain from the calculation, and followed by, now we will proceed with the result and validation section. Previously, we have accomplished the objective 1, which is to model and simulate the bidirectional EV charger model. And now we'll proceed with the results we obtained from the simulations. Now we are going to analyze the variation in voltage and current across the grid during the bidirectional EV charging operation. So this is actually a combination of grid voltage and current during the charging operation, which actually we are looking for the variation in the phase shifting. So from here we can see the grid voltage and current measured for pi cycles. So this is the individual ones. For pi cycle, the voltage, this is the current. And this one is for the discharging operation, which is measured across the grid, the front end. And this is for the discharging operation, the grid voltage and the current measured for the pi cycle. Okay, these are the measured values from the waveforms for the both charging and discharging operation, G2V and V2G. For the maximum grid voltage 325.30 watts, minimum voltage is negative 325.30 watts, peak to peak is 650.60 volts, RMS grid voltage is 230.01 volts, and it's the same for the both case. For the grid current, for the maximum current is 40.99 amps, and the minimum grid current is negative 40.99 amps, and the peak to peak grid current is 81.98 amps, followed by the RMS grid current is 28.98 amps, and then it's the same as well for the discharging and charging operation. Now we have tabulated the grid voltage and current respective to intercept during the charging operation, which is using the zero crossing method or the x-intercept on the axis of waveform. From here, we justify further by calculation that the grid frequency is operating at 50 Hz using this formula, and this is the calculation did for measuring the phase shifting, which is 0.95 power factor with a phase shifting of 18 degrees with a power factor of 0.95, and this is for the discharging operation. And we justify again that the grid frequency is 50 Hz and with phase shifting lesser with 2.7 degree and 0.99 power factor. And this is the analysis we did for the measurement. From here, we can justify that this design is in compliance with the Malaysian Grid Code for Peninsula 2020 amendment, which it fulfills the minimum condition where the degree of phase shifting is within the limits. Next is the result for the battery voltage during charging, current and state of charge, and similar for the battery voltage during discharging, battery current, and also state of charge. And this is the tabulated values, and for voltage, for the current, and also for the state of charge. During state of charge, We can observe there's an increment of 0.016 and also decrement of 0.016, and it is equal. Here we can justify further that and evaluate that the charge is operating properly. For the tool limitations, the simulation time is too long due to complex circuit and sampling time. Approximately 1 hour plus per simulation assumes ideal component behavior, which may differ from real-world hardware and prototype. Third is the computational limit in simulating large-scale or real-time scenarios. In conclusion, the learnings is the tool is powerful for system design and performance evaluation, but limited in capturing real-world uncertainties. The strength is its high accuracy, ease of integration, industry relevance. Constraint is lack of real hardware validation, simplified modeling of environment effects. Future work should include hardware prototyping and further research.